Knapsack is an optimization problem. We have n items. Each item have its weight and price. And we have a knapsack of some size, which indicates how much weight it can take. And we want to take collection of items with biggest price so that they fit in our knapsack. So how we are going to solve it? Well, there are a couple of ways, but we will use dynamic programming. So the idea is to count what items can I take for all knapsack sizes from 0 to b, and use previously computed rows to compute the next one. I have a pseudocode here to help. The first thing is to fill the first row and column with zeros. Why zeros? Because when we have knapsack of size 0, we cannot put there anything. And if we have no items, the price of items will always be 0, no matter what knapsack size we have. We are going to use these data to compute other cells of this table. So, for every item, we go through every knapsack size from 1 to b and fill the corresponding cell. Wait, how do we decide what to write to our cells? Well, if you look at the pseudocode, you can see some if condition. C stands for current knapsack size and W of I stands for weight of element. So, if our current knapsack size is smaller than weight of item that we want to add, we cannot add this item, so we take the number from above. But if we can add this item to knapsack, we have to figure out if we want to do that. Since we want the price to be biggest, we take the maximum from cell above and sum of price of our item and the cell from row above and weight of our item to left. Why is that? Well, the first option says that this item is not in the best solution for current knapsack size. The second means that this item is in the best solution for current knapsack size. And why we are moving by weight to left? Well, since this item is in solution, it takes up some space. And the row above shows us the best price for every knapsack size if we could add only items above. And the remaining space in knapsack after adding current item is current knapsack size minus item weight, what basically stands for cell one row above and on left by weight of current item. So let's fill this table. We are trying to add items with weight equal to 1. The knapsack size is 1, so we take max for cell above and sum of price of current item and cell one row above and weight to left. As you can see, I have been playful with colors, so I hope you understand it. Obviously, 2 plus 0 is bigger than 0, so we write 2 and continue with bigger knapsack. Now, size of our knapsack is equal to 2, but since we can put there only this item, the price is still equal to 2. As you have probably figured out, all other cells in this row will be equal to 2. Let's move on to next item. First, we compare knapsack size with size of our item. Since knapsack size is smaller, we cannot add this item, so we just write whatever is in cell above. Now, the knapsack size is equal to size of our item. But since the price of solution without this item is equal to price of solution with this item, we write 2. But knapsack size of 3, we can fit there more items, because if we take item with weight 2, we still have space for item with weight 1, so we write 4, which is the sum of price of these items. And because we have combined all items we can, the other two cells will have same value. Let's move to item with weight equal 3. For a knapsack smaller than 3, we write numbers from cell above. But when we reach 3, we find out that this item have better price than combination of items above, even though this item completely fills our knapsack. In next run, we can even add to this item the item with weight 1, right? So combined price of these is 7. And same goes with the last cell. Let's go to our last item, and since its weight is equal to 4, for knapsack sizes smaller than 4, nothing will change. When we reach 4, we compare price of cell above and see that it is bigger than price of our item. And if you think about it, it's right, because if we fit this item to our knapsack, we get price of 6. But if we fit the item with weight 3 and 1, we get price of 7, which is more. And in the last cell, we write 8, because that is the best price we can get. For knapsack of size 5, if we can take any combination of these 4 items, we get at most price equal to 8. Now, if we want to figure out what items we should take, we start from right bottom cell and compare this cell to cell above. If the value of this cell is bigger, we add this item to our solution and move left by weight of our item. If it is equal to number above, we just move 1 row above. So let's do this. 8 is bigger than 7, so we add this item to our solution and move 4 cells to left and 1 cell above. 2 is equal to 2, so we move above, where the same thing happened. So once again we move to cell above, where we find out that 2 is bigger than 0, so this item will also be in our solution. And we have reached the top row, so we are done. The best solution is to grab items with weight 4 and 1.